we didn't talk about transfer sensitivity. Okay, we are assuming that the measuring direction is the right measuring direction. However, we have to take into account that there are some sensitivity in the transverse measuring direction, and such sensitivity is about some percent. Okay, that is very large sensitivity, high sensitivity with respect to the strain gauges, for example. That is, remember, less than percent. Okay, 0.4, 0.5%, remember. Okay, in this case, we have some percent, so we have large sensitivity. However, that is not that important if you locate, if you place your accelerometer with a little bit of attention when referring to the
Okay, good morning, everybody.
Okay.
Welcome back. Please give me feedback that you can
this
hear
is
me.
the typical
See the screen.
noise that is affecting your measurement in the laboratory. And I
Okay.
always ask you,
before going on, I would like to tell you
if
two
you
things.
remember, we just talked about
one is concerning the laboratory activities. Because of the rules, the government rules, it is better that you not attend in laboratories, okay, in order to prevent the spread of the COVID-19. So in order to have you experience these kind of activities, I'm going to record the laboratory activity, and then I'm going to broadcast these recordings, and of course with my comment, okay, so that it should be not the same, but you should have a taste of what could have been the laboratory activities. Okay, then I share with you the data that you virtually will record, and then you have the tools to write your own report. Okay. Maybe tomorrow I start the recordings so that maybe next week we can have the first virtual laboratory activity. Okay, that once again it will be in a sort of video broadcast of the activity in the lab. Of course, if you are here, meaning that if you are in the faculty when I'm recording these classes, maybe you can attend just to see what's happening there, but it is not mandatory, of course. All the data, all the discussion will be done together during the video broadcast. Okay. The second is that I'm going to propose you a sort of self-assessment test. Okay, just to, let's say, give you an idea of what is your course experimental testing so far. And I'm planning to have this self-assessment test the next week, Friday the 6th, I think, if I'm right. Okay, and this test is just sort of simulation of what could be some final exam questions. Okay, and therefore you have just to review all the material that we covered together during the classes, and then practice with some formulas, practice with some theoretical aspects, and then try as much as you can to answer the question that I'm going to give you during the self-assessment. It is a self-assessment, okay, thus there is no formal graduation for me, for marking for me, grading for me, but it is just for you, okay? So you can evaluate yourself, okay? And of course, if you have questions, if you have some doubts, we can discuss that the week after, okay? Where I'm going to discuss with you the whole self-assessment, okay? Say again? Oh, no, no, no. Oh, we could also have it. I mean, that's the same. That's the same. I mean, exam.net is because when we are having the final exam, I have to be sure that you are not, let's say, surfing around the net. Okay, and that's the reason why I'm using exam.net, because it's a self-assessment. It's for you. If you if you are cheating yourself, it's your problem. I mean, I don't care about that. Yeah, I can give you the PDF file for sure. Yes. Okay, for sure. Okay. And of course, for people that are attending in person the class, then I can give you the PDF in the class. Okay. On the contrary, I share with the exam.net or via email. I give you the file, okay, the PDF file. Okay. Any question from the audience at home?
Professor, how we can attend in the laboratory that you want to record? I mean, when
There's no requirement. There's no need that you attend the laboratory. Okay. For those people only that are for any other reason here in the faculty, if they would like, they could attend what we are going to do, but the actual laboratory activities will be video broadcast for all of you. So it is just having a sort of first insight by attending the laboratory, but it is not anything formal. Okay. So everything will be discussed together during the video broadcast during our normal classes. I don't know when, because I have to record that, editing a little bit, but I mean, maybe next week we will have our first laboratory activity. Okay.
No, I understand this matter. When do you want to record? I mean, you said that if we are in a university, we can participate in laboratory, and I just want to know when is that. So
Maybe tomorrow morning. I have not an extra schedule about that, but maybe tomorrow morning and the day after, so on Thursday. Maybe the
okay.
first and second one will be tomorrow and Thursday, but I'm not sure. This is why if you are here, you can just email me and then I can reply on the fly. Come join us in the laboratory. Okay. Any other question? Okay, so let me. Okay, so.
Scusi professore, ma ci sarà da fare qualche report, giusto?
Reports are not mandatory, as already told you during the first class. Reports are for your amusement, if you like. If you write all the reports, then your final exam will start with a question concerning your report. Okay, then maybe we can discuss together what you got during the final exam. But that is just a non-mandatory activity. It is just for you to have just a feeling on how to write a report, what are the problems in real life, in laboratory, okay? And if you want a feedback from me, just ask me and then I'll give you, okay? The exam, as I already said, would be oral, okay? But because of the final exam conditions, I'm not sure if I keep going on having your oral exam in a written way. So instead of asking you oral question and having your oral answer to me, you have just to write it. Okay. For this reason, I'm not going to ask you during the final exam a specific solution of a problem. Of course, I will ask you some general question. For example, tell me something about strain gauges. What is the working principle? Tell me something about the different configuration, the strain gauge measurement by using the Wheatstone bridge. Something like that. The more you write, the higher will be your final grade, of course. Okay. Okay, but I'm not for sure asking you if you have a specific strain gauge with that sensitivity, with that strain gauge factor, and that is the output, what is. So no calculations in general, no specific calculations. Is this not just an exercise? It is an oral question, okay, to be written, okay, because of the conditions. Okay. But I will confirm you, let's say 1 week or so before the final exam, because it depends on the corona. Okay, so having said that, acoustic measurements is now the first, the other topic that we are going to consider. consider together today. And what are acoustic measurements? Acoustic measurements refers to the measurements of acoustic waves, okay, and are carried out by the measurement of change of pressure. So this is, to me, acoustic measurement. So let me write that. It's a measurement of acoustic waves done by the measurement of change of pressure. Okay, change of pressure traveling in a media. Okay. And this media could be whatever, air, as we are used to consider, but also liquid, solid. Okay, these are the media that we can consider. But the most important things to remember in acoustic measurement, and that is not the measure of a static pressure. We are measuring oscillation, perturbation with respect to the static pressure. That's the reason why I specify the change of pressure, okay? This change of pressure is perturbation with respect to the average pressure and is giving me the information of the acoustic property of my information that is traveling in a media, okay? In doing that, we are considering three typical quantities, okay, in the acoustic measurement. So the typical quantities are the sound power, that is generally denoted as W, the sound intensity, generally denoted as I, and the sound pressure. And it is generally P, okay? By the way, please remember sound power, watts as unit of measure. So intensity is a sort of density of power, so watts over square meters or watts over square centimeters or whatever. These are the typical unit of measure. And sound pressure is Pascal. Okay. Please note that also that W, that is the sound power, refers to the measure of the total acoustic power that is radiated by a source. Okay, so let me write that. W is the measure of the total, acoustic power radiated by a source. On the other side, we have the I and P, that is the sound intensity and the sound pressure, that specify the acoustic disturbance, okay, that is produced at a point. So different physical quantity. W, the power, is something that is total from a radiating source. I and P, intensity and pressure, is referring to the specific acoustic disturbance.
Okay, we are referring to the perturbation, variation of the quantity. Okay, that is produced, of course, at a specific point. These quantities I and P depend on many parameters. Okay, the first one could be the distance from the source is dependent on the losses in the intervening air path. They depend on room effect if we are characterizing an indoor measurement. Okay. Now, such a measurement, such a acoustic quantities, is a very wide range physical quantity in terms of variation, in terms of values that this quantity is having. Okay. When I'm saying that wide range, I refer that there could be, let's say, 10 to 5 differences, okay, in the order of magnitude. That's the reason why, in order to characterize such quantities, we use a logarithmic scale, okay, in order to take into account as much as possible all these different values from the lower to the highest. There will be a difference of 10 to 5 number, okay, in order of magnitude. So let me write that, because of the wide range of sound pressure, power, and intensity, and so on, that we are going to have, that we are going to hear, for example, using our ears. Okay, so to which ear respond. Let's say you can easily see by yourself that from a whisper to a sonic boom, there is about 10 to 5 in variation of these quantities. Just to give you an idea of what is the lower value and the highest value, okay, that we can hear. If you are referring to acoustic, then there is called the ear to be considered. So when referring to this, a logarithmic representation of scale is used. Okay, and because, as you know, the argument of any logarithmic functions is a dimensionless quantity, we have to refer to some reference quantity to characterize our sound pressure level, our sound intensity, and our power. Okay, and these quantities, these reference quantities, are W0
that is the reference sound power, are I0, the reference sound intensity, and P0, the reference sound pressure. The reference power, sound power, is 10 to negative 12 watts. I0 is 10 to negative 12 as well, but watts over square meter. And P0 is 2 to 10 to negative 5 Pascal. Okay, these quantities are not derived by something strange from the physicists, but they are referring to the weakest sound that a man can hear when vibrating at 1000 hertz. Okay, so this quantity to the weakest okay. On the other side, the sound pressure level reference value, P0, is the sound pressure at the threshold of such a hearing, okay, once again at 1000 hertz. Okay. So we characterize these reference values, okay, in terms of sound power reference value, sound intensity reference value, and sound pressure intensity value. Why that? Because of the wide range of variation of these quantities, we need to use a logarithmic scale, and the logarithmic scale needs a reference value. Okay. Now, let me introduce such a logarithmic scale. The logarithmic scale starts by the definition of the Bell value. The Bell value is defined as the logarithmic base 10 of the ratio of the two quantities, let's say x1 with respect to x0, that is the reference value, and the decibel is as well defined as 10 logarithmic base 10 of the same ratio. Okay, so these two are related. It is just a matter of 10. Okay. Because of that, now the previous quantity, the power, the intensity, and the pressure, okay, are referred to the levels of such a quantities in such a logarithmic scale, such a logarithmic representation. Okay, and thus, having introduced the Bell and the decibel, we are defined that the sound power level as LW as defined as 10 logarithmic base 10 of the actual power with respect to the reference one. Okay. The sound intensity level is defined as Li that is 10 logarithmic base 10 of I over I0. And finally, the sound pressure level is defined as LP, that is 10 logarithmic base 10 of P over P0 square. Okay, and because of that, it is also represented as 20 logarithmic base 10 of the ratio P over P0. Okay, let's discuss this last definition. Oh, better, let's start with the first one and the second one, power and intensity. Both power and intensity are all positive quantities. Okay, both W, big W and big I are positive quantities that are referred to the W0, the reference, and the I0, the other reference for the intensity. Okay, when referring to the pressure, as I said before, I'm referring to oscillation, perturbation with respect to the base. Okay, so it could be whatever number. That's the reason why when referring to the pressure, we are referring to a quantity that uses the pressure, but it is referring to, let's say, the energy that your acoustic information is having, okay, in that point. So that's the reason why we are using the square here, such a definition. Okay, let me have a remark on it here. Okay, this P square is proportional to the acoustic energy. Okay, and just to give you an idea of the quantities that we are going to use, and if, and that could be, not if, because, sorry. Okay, and because the pressure is proportional to the intensity, okay, when we consider the mean square value of P, that is a function of time, then P is replaced by P in RMS. Okay, so that's the reason why when referring to the sound pressure level, okay, we are referring to the square of the ratio of such pressures, okay, that is a perturbation quantity. Such a pressure are proportional to the sound intensity, and if that is true, then we can use as a reference value the mean square, okay, and thus generally when referring to the sound pressure level, we are referring to the pressure in terms of RMS value, okay, RMS in the observation time, okay, and that's the reason why, by the way, that the two levels, sound power and sound intensity, are given in dB, decibel, with that representation 10 times logarithmic base 10 of the ratio. The sound pressure level is 20 times logarithmic base 10 of the ratio of the pressures given in RMS. Okay. Just to have fun with these quantities, just to have a touch of these quantities, let's consider what happens.
Sorry, Professor, can I ask you a question about
Yeah.
P?
Yep.
Okay, you said that P could be negative or positive.
It is the perturbation with respect to a reference value. If you have a zero reference value, that could be positive and negative. Okay.
Okay, and so if we have a negative P, so I think it is not true to bring the power as a factor. I mean, we should put the square the way it is. We should not write 20 logarithm.
No, that is the reason why we are using the square. Okay. Here, here, over here. Yes, by doing that, we are assuming just the amplitude of that. Okay, so the sign is removed completely. We're moving from 10 logarithmic base 10 to 20 logarithmic base 10. Okay, but the most important thing is that in that, because P is proportional to the sound intensity, and when we are considering the mean square, we can, let's say, use the RMS value instead of the actual quantity that is more representative. Remember, we are referring to a perturbation, so something that is dependent on time. Okay, so you fix the observation time and then you calculate the RMS value and then you use that in order to evaluate the sound pressure level. Okay.
Okay, thank you.
Okay. So if you want, you can have here as the absolute value, but it's the same. We're moving from the upper to the lower one. Now, if we are having the intensity of your sound, of your acoustic quantity that is equal to the reference one, that means that the level Li is equal to 0 dB. Okay, so please remember, when you are referring to a 0 dB quantity, that doesn't mean that there is no signal. Okay, so let me remark. Okay, then let's consider another condition for which the actual sound intensity is twice the reference value. The level, the sound intensity level is 3 dB. Okay, that means that the doubling the level means an increase of about 3 dBs. Okay, but we can also see the reverse. If we have half the level, that means about negative 3 dBs. Okay. If you do the same thing for the pressure levels, okay, that means the level, some pressure level is 6 dBs. Okay. E equal 1/2 0 at negative 6 dBs. Okay. Another interesting evaluation is what happens is referring to the intensity, sound intensity, when there is an order of magnitude in difference. So I is equal to 10 I0 with respect to the reference one. That means that the sound intensity level corresponding to this one order of magnitude increase is 10 dBs. Okay, that is a ratio of 10 corresponds to a level difference of 10 dBs. Okay, I would say also regardless the reference value. Okay, now a question for you. If we are having I equal to 10, 100, sorry, I0, what happens here to the sound intensity level? 20 dB. Okay, that's the reason why we are using a logarithmic scale. 2 order of magnitude is still represented with the same scale. Okay, 10, 20, 30, and so on. Another very interesting game that we can have just by having fun with this logarithmic representation of these acoustic quantities is what happens if we make the product of these two references. For example, what is the intensity, sound intensity level of the product of two quantities? For example, P1 with respect to P0 times P2 with respect to P0. That is equal to the sum of these two. Okay, that comes straight from the property of the logarithmic function. Okay, that is the level of the product of two ratios is equal to the sum of the levels for the two ratios. Okay, you can enjoy yourself. For example, if you have something like this, 2 times 4, you would like to have the evaluation of the sound intensity level. Okay, that is equal to the sound intensity level of the number 8. That is about 9, but that is also equal to this. Okay, and plus 6, about 9. Okay, just let's say enjoy having fun with these numbers. But the most important thing is that you can, let's say, in this decibel scale, you can add quantity that's represented in multiplication in the linear scale, okay, as we are used to. Now, this table that now I'm going to draw just for having a let's say a common reference is common available in the internet, so the web you can find lots of that. But just to to show you some typical sound pressure levels, I'm just going to write this. So typical are, for example, we have SPL here, and then type of source. So 0, a sound pressure level equal to 0. We already discussed that, is the audibility threshold. Okay. By definition, because we are referring to the minimum quantity that the ear can hear. Then about 50, a sound pressure level equal to 50, is the typical home office sound related activity. Okay. 60 is, or SPL, of course, I would like to stress this, but these are the B's, of course. 60 is the normal conversation. 70 is the traffic. 80 is specific for Rome, heavy traffic. 100 is a jackhammer. Or for those like me that likes to go to rock concert, is a typical rock concert. Sound pressure level if you are just in front of the stage. For example, 120 dBs is the check engine. 100 meters apart as all the other wires. Okay. And here I can also remark that it could be possible hearing damage. Uh, 130 is the threshold of pain. 160 is the sonic boom. A little bit higher, 170 is the sound pressure level of a rocket launch. And I would like also to emphasize the fact that 194 is the 1 atmosphere pressure. This is just to remark you that these quantities, the acoustic measures refer to the perturbation. Generally, we live with a 1 pressure, atmospheric pressure, or one atmospheric pressure. If you oscillate with that amplitude, okay, then the sound pressure level is equal to 194 dBs. Okay. So that is the typical levels for the SPL characterizing our, let's say, typical activity. That could be very nice to refer. Now, these quantities are sort of, let's say, analytical quantities. We can use some transducer microphone, for example. Okay. in order to measure such a quantities. But if you are interested, as in general we are when doing such acoustic measurement, to the effect of these quantities to your human activity, then you have to take into account of the ear system. The ear system is strongly non-linear, okay, and depends human by human, okay, human being by human being. It is not just a simply one-to-one transducer, okay, and that is good. For example, if your ear system is receiving from your friend the sound pressure because he's speaking, and if there are, let's say, 1,000 friends that are speaking all this at the same time, just in front of you, for example, when you are in a concert, even more than 1,000 people, if your hearing system is linear, then maybe you can break everything. If your hearing system is non-linear, okay, then all these voices together are lost sort of attenuated, okay, by the non-linear system, and therefore you can hear without any problems all these people speaking, okay, and that is the reason why there is a labyrinth inside the hearing system that is sort of let's say logarithmic scale, okay, real life logarithmic scale. However, it is very interesting to characterize how the human hearing system is, let's say, receiving, is feeding the acoustic source, okay? And that's the reason why we are dealing with the perception of this general loudness that is around us. So this perception, focusing the attention now from the human ear system point of view, we have to characterize such a perception. And thus, the perception, we have to consider that the perception of the loudness, okay, that is the result of the acoustic quantity, the result of this information that is traveling with the acoustic wave, strongly, as already said, depends on human ears and is different with the change of frequency. Also, it depends on the age. And that is what we are going to discuss a little bit, okay? Once again, now we are evaluating what is the effect of the acoustic quantities from our side, from the human being point of view, okay? Why this? I don't know if you ever flew with prop aircraft, okay? There is a lot of noise inside that with respect to, let's say, jet engine based aircraft. It is a very smooth, quiet flight, okay? And if you take some acoustic measurement inside the fuselage of a prop aircraft, maybe the quantities, the levels, the Li, Lp, and L that we can have, maybe are not that high, but however, the perception of such acoustic quantities is noisy for us, is making us have a headache for, let's say, an entire month, for example. Okay, so that's the reason why we are going to analyze these effects from the human ear point of view. And as I told you before, it is a nonlinear system, nonlinear not only with respect to the different values of the acoustic quantities, logarithmic scale, but also it is nonlinear with respect to the frequency. What does it mean? That the effect that acoustic quantity is having on the human ear, or human, when vibrating with a just one frequency, could be completely different when the same amplitude of vibration, so same Li, is vibrating at a completely different frequency. Okay. Moreover, you as young man and woman are characterized by having a higher sensitivity to the acoustic waves with respect to me, that I'm still young in my heart, but not that young from the physical point of view. So my earrings are a little bit less sensitive to with respect to your hearing. So also this is a factor that I have to take into account. So in order to characterize this perception of the acoustic information, the acoustic noise, vibration, perturbation of your media, okay, we are defined what we call the loudness curves, okay, and this loudness curve is a result of a large number of tests that have been carried out once, okay, and these tests take into account several parameters, all referring to the psychoacoustic experiment. So there is a source, and there is a man or a woman with a prescribed age, okay, that is telling something concerning the perception of that acoustic pattern, okay? And then we collect all this data together in order to produce such a loudness curves. Okay, now let's see just very briefly, in principle, what are these tests that have been carried out in order to produce these loudness curves. Okay, so loudness curve is a result of a large number of different psychoacoustic experiments and parameters of these experiments are the following. First, type of sound source. Okay, so we made a lot of tests trying to characterize the effect on the UNC being of sound source, different sound sources. These are mainly the pure tone, it is just a pure harmonic vibration, a prescribed frequency, or frequency band, having various widths. Okay, so different type of source, pure tone or a composition of tone. Okay. Other parameters refer to the sound field that could be subjected maybe in a free field or in a reverberant. Okay. Moreover, the stimulus may be applied to one now I think that it will come to one or both ears by means of sources that could be in the room or directly by the earphones. Okay, doesn't refresh. Let me see. Okay. Okay, there you go. Okay. Once we have done all these tests, what's happening is that all the curves are finally statistically smoothed, okay, and average, considering a large groups of people with normal hearings and age group between 18 to 25 years old, okay, in order to have the reference loudness curve, okay. So curves are finally statistically smoothed and averaged. And this is done considering groups of people with, of course, normal hearing in the age group of 18 to 25 years old. Okay. Because of time, let's have a 5 minutes break. Okay. And then we resume the class. So let's resume at 3:25.
Yeah, Professor.
Yes.
Can I just scroll it up, Professor? I have missed some to write.
Yes. Tell me.
Yeah, can you just scroll it up, Professor? I missed some stuff to write, Professor.
You can call me. Yes. Maybe not today, maybe tomorrow.
No, Professor, I missed some part of writing in slide. So I just can I just scroll it up, Professor?
Ah, scroll. Okay. Until where?
Yeah, fine, fine, Professor, fine. That sound field, Professor, sound field subjected.
That at the very beginning of this class, the equivalent circuit is also including the capacity
Yes,
and
but
the
you will
resistance
have the
of the
copies
cable.
on this.
Okay, and here
no.
is the
Okay,
effect.
so
So
don't worry if
why?
you miss
What's
some.
happening? Remember, the accelerometer is telling you what is the output acceleration by generating charges or voltage that are very, very, very small values. Okay. Now, if you consider how a cable is made, and on the right we have a very easy representation of that, we can have that because of the wirings, because of the coatings, we can have that there are some charges, electrical charges, static charges that are on one side of the other side of the coating. Now, if you start having your cable moving, then these charges start moving because change the shape of the coatings and the electrical wires and so on. And this movement will introduce an additional current or charges. Okay, and therefore will introduce some noise in your measurement. How can you solve that? Avoid, as it is very clearly stated on the left side of this picture, avoid any loose cable, tape everything so that everything should be consistent with the test of a specimen. Okay. And okay, environmental effects, because of the sealing, because of the nature on how this accelerometer is manufactured, there is no practical environmental effects to take into account. Okay, not for the humidity, noise, nuclear radiation, magnetic field, corrosive substances, just the base strain. The base strain could be important for the compression accelerometer, compression layout accelerometer, only for that.
Professor, how we can find this document?
I share you with you. I share this with you. Okay. And then here there are
Okay.
some special accelerometers. Okay, triaxial, calibration, high temperature, shock, high sensitivity. So they are maximizing some property with respect to the others because they are special. Okay, so calibration are very, very, very precise accelerometers. They could be used to calibrate another accelerometer so that we compare just the output functions between the calibration accelerometer and the other accelerometer, and then we found out the sensitivity of the other the unknown accelerometer with respect to the calibration one, so that we are sure what is the biasing constant that is transforming the output voltage into the acceleration. Triaxial is very useful because we can attach that accelerometer in one point and having at the same time the measurement in the three reference direction. Sometimes it is very useful. High temperature and shock, we already discussed about that. Sensitivity also, if you are referring to very low value of accelerations. That is typical of my degree thesis student. They don't care about the accelerometer, so it happens that sometimes the accelerometer falls down, then could break everything. So please handle with care the accelerometers because they are very sensitive. Although they seem very robust indeed, but internally the moving mass could be very
Okay,
sensitive.
now
So
let's resume the class. We had defined what are the parameters that have been tested when producing the loudness curves that are sort of representation on how the human ear system is perceiving the external sound vibrations, okay, the acoustic vibrations, and the tests, how the tests is. Okay, test consists in evaluating the sound source at different frequencies. Okay, how that is carried out. The amplitude of the source is varied, generally from low to high values. Okay, until the subject perception of the amplitude is the same as the reference tone at 1000 hertz. Okay, so the way this test is carried out is that, for example, let's consider just a single tone. Okay, you are wearing the headphones, okay, and then you are hearing one reference tone at 1000 hertz with a given amplitude, okay, so that you, as a test man, as a test subject, are memorizing in your brain that level of amplitude. Then we change the type of source. For example, we change the frequency, and we send to your headphones this signal at very, very low amplitude levels that you barely can hear that. And then we increase that level little by little until your perception of the amplitude is the same as the reference tone that you were hearing before. Okay, once you are perceiving the same level, then you stop the test. Then you tell the technician that it's okay. The test, the new tone is having, from your point of view, the same amplitude as the reference one. Okay, and that you go there at different frequency, different amplitudes. Okay, until you have a sort of plot. Then you average everything with the other friends that you got, women, men, and so on, in order to have a general trend, as we already discussed. The results of this test are the so-called auditory sensitivity charts, or loudness charts, or plots, whatever. Okay, the line that is having the same perception of the loudness are called phone lines. Okay, that is, these auditory sensitivity chart are measured in phone. Okay, that is lines that gives a constant level auditory perception as a function of frequency. Okay, but as I said before, these loudness levels are normalized. Okay, so that it results that the phone levels are different from the SPL levels. Why that? Because there is the human perception. Okay, so the phone levels are referring to the human perception, whereas the SPL level are referring to the instruments. Okay, now I'll show you, and also I'll share with you such a chart, such a plot. Is oh, sorry. Yeah. Here it is. Okay, so here is your loudness plot. Okay, as you can see, we have in the x-axis the frequency, logarithmic scale. In the y-axis, we have the SPL, okay, the sound pressure level. Okay, by the way, in that chart is also reported for convenience the reference sound pressure level. That is the one that I told you before. Okay, what does it mean? That it means that each horizontal straight line represents what is the source the instrument doing for us. Okay, now let's focus on the curves. These are the actual loudness level curves. Okay, and this represents the human perception. What we can see is that first 4,000 hertz approximately, okay, those sound pressure levels are having a minima, okay, all the curves. That is, in that frequency, the human ear system is characterized by the most sensitivity frequency. Okay, so what I can say is that here we are having at about 4,000 hertz. Okay, there is the ears most sensitivity. The ear most sensitivity frequency. Why that? It's because our frequency, talking frequency, is about 4,000 hertz. So our ear system is optimized for a better understanding of what you're doing, for a better understanding of what are, let's say, this sound, the wood, this sound for hunting, and so on. Okay. From this point of view, we can see that a very, very, very low frequency and a very, very, very high frequency, there is a fall off of this sensitivity. Or we have a sudden rise here and there, okay, of this loudness plot. Okay, for this case, what we got is that there is a fall off of the ear's sensitivity. Okay. Moreover, when referring to very, very high frequency, for example here, we can change color. Here. What we got is that tones at those all frequencies tend to have similar loudness. As you can see, those curves are going to have the same values. Okay. Okay. That is an additional assessment that the ear system is fully nonlinear. Okay. And depends very much on the frequency range. Okay. How can we use this chart, for example? So let us now pretend to be a test engineer trying to evaluate such a course. And here, for example, we can say that consider now that we are having a sound pressure level source of a certain value. Let's say, for example, here 40 dBs here. Okay, 40 dBs, change curve. 40 dBs. That corresponds, by definition, to a sound pressure, so to a phone curve, so a loudness curve of 44. Okay, why that? If you remember the test, you are given at 1000 hertz a tone whose amplitude is considered as the reference. Okay, that's the reason why at that frequency, 1000 hertz, the phone loudness level is the same as the sound pressure. Okay, then what happens if we consider tones of different frequency? For example, here I got 50 dB tones at 1 kilohertz. Okay, is equal, is 50, so a little bit higher, so this one is having the same effect just by following this curve. Okay, these blue lines here. And there. This is 50. As you can see here, these 50 dB tone, yes, 50 dB tones, is equivalent when referring, for example, to 50 hertz, so 10, 20, 30, 40, 50 here. Yeah. Is about 73 dBs. So this chart, this plot is telling me that 1000 hertz tone having a 50 dB amplitude is equivalent to a 50 hertz tone, but the amplitude is higher, to 73 dBs. Or if you increase the loudness, the frequency, sorry, and you go up to 4000 hertz, yeah, you have about
42 dBs. Okay. So that is how we play with different sensitivity regardless of the human hearing system. So if you have just a simply, here we got 50 dB tone that your microphone is using, we have a completely different effect from the hearing system point of view at different frequency. Lower frequency, okay, at lower frequency, we feel that we need to have 673 dBs in order to have the same feeling. That is, we have to increase the volume, if you want, at lower frequency. On the contrary, at higher frequency, we have to reduce the volume to have the same feeling. I don't know if you are familiar with the home theater system at home, then you have the equalizer, whatever knobs and whatever things. It is very usual that you increase the value of the bass, okay, and reduce a little bit the high frequency gains when you are hearing the music. Then there is a matter of taste of different persons by persons, okay. But generally, the bass, the lower frequency content is increased, okay. And that is the reason why, because your human system, your hearing system, is having lower sensitivity with respect to what you're having. And that is, the loudness curve is telling you this. And it's quantifying how much is this increase in level at different frequency. Okay. Now, just to end our class, I would like to show you, and I will share that with you. Okay, I would like to show you the measuring chain for such an acoustic measurement. So the measurement generally are using microphones. I'm not going to enter into the many details of such a microphone, but these could be viewed as transducers that produce an output tension that depends on the sound pressure. Okay, and the accuracy is plus minus 1 dB. Okay, so the general measuring chain is having your whatever input pressure. Once again, it is a perturbation. Okay, it is not a static pressure, otherwise we can't hear anything. Then we got the microphone. Okay, and as I already told you, the output of this microphone is an output tension. Let me call that E0. And that E0, the output tension, is very, very, very small. Okay. So what we got, we need an amplification of that. So we go to an amplifier. Actually, it is generally referred to as pre-amplifier, but now let me stay on just the amplification stage. Okay. And the output is once again an output tension, for which of course E1 is higher than E0. Then we have to introduce the human hearing system if we like to characterize such a traveling wave, such acoustic information from the human being perspective. So what we got here is what we call a weighting function A, B, and C. I'll tell you something more on this weighting function just in a few seconds. Once we weight this measurement that is E1, the output is E2. Okay, and E2 is representative of what could be the human hearing system perception. Then E2 is even further amplified. Okay, so that we enter your whatever analysis tool with the right output tension, input tension. Okay, so for example, we can have here, for example, filtering. Okay, and then, for example, E4, we can have for example, post-processing like RMS and whatever, okay, and other options. Okay. What are these weighting functions? Weighting functions, as already said, take into account the ear system. That is the loudness curves that we already discussed. Okay. So what we can say is that your measurement is sort of filtered with respect to the loudness curve, so that we emphasize or we fade at different frequency your signal, so that it is more representative of what we will feel by hearing that kind of source. Okay, and this filtering happens at different phone levels. Okay, so we got what we call the A field weighting, correspond to the 40 phone loudness curve. The B weighting correspond to the 70 phone curve. The C weighting correspond to 100 phone level. Okay. And I could also add a D curve, D weighting, that is typical for aeronautical use, is
for single event aircraft noise. Okay. And these curves are more or less, now I'm going to try to plot them. We have the frequency, we have the relative response in terms of dBs, start from 0. Okay, then negative 10, 20, 30, up to negative 70. What we got here is something like this. Frequency start from 10 hertz, 10 hertz to 5, 10, 10 to 5, then 1000, and then 2, 5, and then 10,000, so on. Okay, like this. So the plots are all passing through 0 almost. Like this. Then we have this one, 40. There's some difference over here. Okay, that is A, that is D, C, and D. This is B, and this is A, D is there, and there is also the C over here. Okay, approximately. Okay, so for different frequency, you have this action of filtering, okay, of weighting, actually, better than filtering. So each frequency is given to this. By the way, these curves, A, B, C, D, are, if you want, the inverse of the loudness curves, okay, evaluated at different phone levels, as I told you. Okay, so when you are going to take some measurement in the acoustic field, please remember that such measurements are not representing what is the human perception, okay? Because the human perception is strongly nonlinear from all points of view, also with respect to the frequency. So in order to have a representation of the human perception, you also need the loudness curves. The loudness curves, we talk about how these loudness curves are obtained from the test activities, okay, but are curves that are representing the same perception of your sound source at different frequency. And these loud curves are, let's say, assessing the the non-linearity of such a system. They are assessing me the difference in the behavior in the human hearing system behavior at different frequency, lower frequency, very low sensitivity, high frequency, low sensitivity, but not that high. The best, the high sensitivity we got at about 4,000 hertz. And we can have different SPL level, that is, the sound source could have different values in order to have the same perception. Or if you reverse the analysis from the test engineer point of view, you can have different effects of the same amplitude sound source at different frequencies. Okay, this is the typical measuring chain. Okay, that is including the microphone, the first preamplifier stage, then the weighting A, B, C, D for aircraft. Once again, amplification, and then filtering, and then you can do whatever. Okay. Questions? Okay, so thank you so much. Start reviewing the material, the stuff that we cover so far, so that the next week, Friday next week, you are up and running for the self-assessment. Okay. Thank you. See you on Friday.